Okay, people, welcome to section 3.7, related rates. The title is related rates, but really what it should be is word problems with implicit differentiation. Okay? All right, so we only have two objectives, and that is to find a related rate and to use related rates to solve real life problems. Although, as we all know, that phrase right there, real life, there are extensions to these applications here that could be seen as real life problems, but these are going to be somewhat simplified. Okay. All right. So, finding related rates. Related rates are word problems that contain variables which are changed with respect to a variable that is not included in the equation. Wait, what? So, related rates are word problems that are going to contain variables, and those variables are changing with respect to a variable that is not included in the equation. Let me give you a real simple example. Suppose that you have a pond. This is my drawing of a pond. And you throw a rock into the pond. That rock is going to cause ripples, concentric rings, to grow, to come out of there. And those rings are all moving out from that center. Right? And if we look at any one of those rings can be thought of as a circle. And so we could have the area of one of those circles would be pi r squared. And in that equation, there are two variables. There is a variable A, area, and there is a variable R, radius. And both of those variables are changing with respect to time. That is, as more time passes from the point of impact of the rock with the surface of the water, the radius is going to grow. So that means that the radius is a dependent variable that depends on time, the independent variable. Okay? Now, if we think of that same circle, the area of that circle is also a dependent variable because the area depends upon time. The area of the circle is a function of time. Or what if we wanted to talk about the circumference? What is the circumference? Pi times the diameter? Okay? There are two variables in that, circumference and diameter. But both of those are changing with respect to time. So time is the true independent variable in this situation, whether you're talking about the area of the circle or the circumference of the circle, and it's not even in the equation. And that's where the implicit differentiation part of this comes into play. All right, let's take a look at another example. Suppose that water is being drained out of a conical tank. So we have a tank over here that looks like a cone. Right? This cone has a height, which is some h, and has r, which is some r, and it's filled inside with water. So in here's water. Right? There's a hole at the bottom, and so water is leaving. That means that the volume of this cone, the volume of the water inside the cone, is changing. Okay? So when water is being drained out of the tank, then the measurable quantities V, R, and H are all going to be functions of time. So even though we have a static equation, V equals pi r squared H, that only tells me the volume of water in the tank at a specific moment in time, because at a specific moment in time, the radius is going to be some number and the height is going to be some number. But when time changes, R is going to be a different number, H is going to be a different number, and V is going to be a different number. Because when time changes, more water falls out of the bottom of this thing, drains out of the bottom of this conical tank. And when water goes out of this thing, all of the measurable variables here, the volume, the radius, and the height, all change. So all are functions that are changing with respect to time. And if a variable changes with respect to time, then we should be able to take the derivative with respect to time. Right? And so if we take the derivative, ddt, okay, so there's our operator, tells me what to do. It says take the derivative and make the independent variable be time. And so when I take that first derivative, that first variable I run into, v with respect to t, the variables don't match, so that's going to be implicit differentiation. So that's going to give me dv dt. Okay? On the right-hand side, I've got a complicated problem to deal with over there because I have two variables, r squared and h, being multiplied together. So I'm going to have to use, what's the rule you use when you have two things multiplied together? Product rule over there. Right? The pi over 3, I'm not worried about that. That is just a coefficient. So if I think of this as the product rule, then that would be the u, that would be the v, and product rule says it's going to be u prime v plus uv prime. Right? So then what is the derivative of r squared to get our u prime? Well, the derivative of r squared is going to be 2r times implicit differentiation, dr dt, because the variables, I shouldn't have colored that in like that. Sorry about that. R and t don't match, right? Times v, which is h, right? And then the uv prime plus r squared times the derivative of h. Well, the derivative of h with respect to t, dh dt, and then I got to multiply this whole thing by the coefficient pi over 3 from out there in front, and that's where we get this 2 pi divided by 3 rh dr dt from that first term, and the pi over 3 r squared dh dt from the second term. Right? So what is this saying? Well, it's saying, and if we read this from left to right, not for the math notation, but for what it's saying that over here on the left, the rate of change of the volume with respect to time can be found by this equation right here. Okay? What's dr dt? Well, it is the rate of change of the radius with respect to time. What's dh dt? Well, that's the rate of change of the height with respect to time. And then, of course, there's some coefficients and some other variables involved in this mess. So these are related rates problems. Related rates problems are word problems for the most part, where you're going to have an equation that is going to contain multiple variables. How many variables? 2, 3, 4, 5, 6, doesn't matter. There's no limit. And all of those variables are going to be changing with respect to a variable that is not included in the equation. Now, it is a vast majority of these problems where the variables are changing with respect to time. Occasionally, you will see other ways that the variables change. But for the most part, when we're talking about these problems, we're talking about variables that are changing with respect to time. Okay, so what's going to happen in this section is we are just going to have application problems where we're going to do this sort of thing. We're going to have a scenario where variables are changing. We're going to be asked to figure something out about this system at a certain point in the system's life, at a certain point in time, essentially. Okay? All right, let's take a look at an example down here. The variables x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. Find dy dt when x equals 1, given that dx dt is equal to 2 when x equals 1. Okay? All right, so I'm told that both x and y are differentiable functions of t. That means that x is a dependent variable and it changes based on what t is. Y is a dependent variable and it changes based on what t is. But x and y can be related to each other with that equation right there. My job is to find dy dt, the rate of change of y with respect to t, at a point in time when x is equal to 1, dx dt is equal to 2. Right? So the first thing I'm going to do is I'm going to differentiate with respect to time. Okay? Left-hand side, obviously the variables don't match, so that's just going to give me my dy dt through implicit differentiation. Right-hand side, right, derivative x squared with respect to t, which of x squared with respect to t is going to be 2x times dx dt, and then the derivative of 3 is just 0. Right? So here's my derivative with respect to time. Right? Here is the part of the derivative that I'm asked to be solved for. I'm asked to find or to solve for dy dt. If I'm going to solve for dy dt, then these values right here have to be given. Okay? And I was told that x is equal to 1 and that dx dt is equal to 2. So I'm going to plug those in, and I'm going to say then that dy dt is equal to 2 times 1 times 2, or that dy dt is equal to 4. Okay? So essentially, this is what's going to happen in every single one of these problems. This one was just the ultra simplified version of it because someone was kind, and they gave us the related rates equation that puts together our dependent variables, and they gave us all of the pieces of information that we might need in the end. Usually, we're going to have to read the problem and write this equation, or solve for that equation if you want to read it that way, and then we're going to have to dig around in the problem and try to find those things. Okay? All right, so let's take a look at this problem right here. It's the one we talked about earlier. A pebble is dropped into a calm pond, causing ripples to form in concentric circles. So these are the circles going out earlier. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. Okay? When the radius is 4 feet, at what rate is the total area of the water changing? Okay, now this is where my reading skills need to get really good with calculus. Okay, so circles, radiuses are increasing at a rate. That tells me I'm looking at a derivative here of 1 foot per second. So here's what I remember from when we talked earlier. I know that area is equal to pi times the radius squared. And area is a function of time. Radius is a function of time. Okay? The problem asked me when the radius is 5 feet, that means when r is equal to 4, at what rate is the total area of the water changing? That is, what is the value of dA dt? What is the rate of change of the area with respect to time? Okay? All right, so first things first, I'm going to take the derivative with respect to time. Left-hand side, the variables do not match. Left-hand side of the equation, the variables do not match. So the derivative of a with respect to t is going to be dA dt, which is exactly what we're looking for. Okay? Right-hand side, pi is just a coefficient, so it just drags along. Derivative of r squared with respect to time, chain rule, 2r times implicit differentiation dr dt. At this point in time, I'm looking at an equation that contains 1, 2, 3 unknowns. If they want me to solve for any one of those unknowns, that is, solve for this one, then the other two must be given somewhere in the problem. And they might be given explicitly, or they might be given in a way that we have to then solve for them to figure it out. Okay? Now, this one explicitly told me that r was exactly 4 feet, so I know that r is going to be 4 feet. Okay? It also told me that the outer ripple was increasing at a rate of 1 foot per second, or that this value right here is going to be a positive 1 feet per second. Now I want to stop there and just remind you of something. Okay? It is rare, exceedingly rare, for a negative quantity to ever show up in a word problem written as a negative number. We will almost always rip that negative symbol out of there and then use words to describe it as being a negative quantity. Right? If in some alternate universe, when you tossed a pebble in a pond, the rings went in rather than going out, then we wouldn't say it had a increasing at a constant rate of 1 foot per second. We would say that it was decreasing at a constant rate of 1 foot per second, which means I need to read not just the 1 foot per second, but I need to know whether that's a positive quantity or a negative quantity. And I need to look for those things and be careful of those things because they do matter in the end. Same thing when I work one of these problems, if I get a negative answer, I need to make sure that I write my answer correctly. Just because it says in the end, the math says dr dt equals -5, that might not be how I write the problem's answer. I might have to say something is decreasing, or something is getting smaller, or something is losing value at a rate of, okay? Because it is very rare to ever leave a negative in a word problem. We almost always pull that negative out and replace it with some sort of terminology, some words that mean the exact same thing. All right, back to this. I'm plugging in numbers. All right, my job was to solve for dA dt, so it stays dA dt. On the right-hand side, I'm going to have a pi times a 2 times an r, which is 4 feet, times a dr dt, which is 1 foot per second, and then that's going to give me, what is that going to give me? 8 pi square feet per second, and that's my dA dt, or the area is increasing at a rate of 8 pi square feet per second. So when I toss this pebble in this pond, here's what's happening. Okay, we're at 16 minutes right there, so I'm going to stop, come back, and we'll come back part 2. We'll start here and talk about the guidelines for doing this, and then we'll do another problem where we have to write everything ourselves. All right, see you back here for part 2.